Hi, welcome to the next video lesson. So we are going to now start 5.1 and chapter 5. So for 5.1, we're going to start talking about functions and inverse functions. Okay, so let's look at this table. Let's call it table 1. Okay, so the first column, let's call it T for hours. And the second column, let's call capital N equals F of T, which is the population at time T. Okay, and so at 0 hours, the population is 100, let's say. At 1, the population is 168. At 2, it's 259. At 3, it's 358. At 4, it's 445. And then at 5, it's 509. Okay, so for each point in time, in hours, we have a population at that time. Okay? And so in table 2, I'm just going to think of the opposite direction. Okay, so let's say the first column is capital N, and T is equal to F inverse of N. And this is the time to reach, this is equal to time to reach N bacteria. Okay? So if N is 100, then we're going to say the time it takes for the population to reach 100 is 0. If we say the population is 168, then the time it takes to reach a population of 168 is 1 hour. This is in hours. Okay. The next row, if the population is 259, then the time it takes for the population to reach 259 is 2 hours. If the population is 358, the time it takes to reach that population is 3 hours. If the population is 445, the time it takes to reach that population is 4 hours. Good. And then if the population is 509, then the time it takes to reach that is 5 hours. Okay, so we have 2 tables here. In table 1, we have as an input into the function, we have a time in hours, and the output, we have a population at that time. And in table 2, we go in the opposite direction, and we start with a population, and we say how long does it take to reach that population. Okay? So in this case, this function t is an inverse of this function f. Okay? So this function t in table 2 is an inverse of that function f. Okay? And so this is representative, this represents the inverse of a function. Okay? One way to represent a function is through a table. Right? So you don't have to only represent a function as an equation, like f of x equals 2x. Right? F of x equals 2x represents a function as an equation. But you can also represent a function as a table. And so here's the table, and this represents a function. And this table also represents a function. And more specifically, this is the inverse function of that one. Okay? And so in this section, you'll learn about an inverse function, the definition of an inverse function, and how it applies to defining a one-to-one function. How you get an inverse function from a one-to-one function. Okay, so this is an inverse function of that function. And so you can see here an example of how you can create an inverse function or get an inverse function. Okay? And so note, I'm going to put a note here, not every function has inverse. Not every function has an inverse. Okay? So in this particular case, this function defined by this table has an inverse function, and it's this one. Okay? You can go in the opposite direction with the function. Okay? Instead of saying you have this input and this output, you could start as your input the outputs of this function, and then say the outputs of this function are the inputs of that function. Okay? Okay, so I'll be more specific about what this means, so we're more general. Okay, so I guess more general as to what an inverse function is. So that's one particular example of a function with an inverse. Okay, so let's change topic 7 for just a second, and let's talk about another concept, which is a one-to-one function. Okay, so you have your function f here, and so f, or here, this function f is a function from this set A to that set B. And so this is a very simple function that maps 1 to 2, 2 to 4, 3 to 7, and 4 to 10. The domain set is A and the codomain set is B. Okay, so for this function, f of x1 does not equal f of x2 when x1 does not equal x2. Okay? When you have two different x values, when you take two different inputs of this function, the outputs are different. So 1 does not equal 3, and also, as a result, f of 1 does not equal f of 3. So whenever you take two different objects in the input function, when you take the images under f of those two elements in the domain set, their images are also different. Okay? So when means this is where you start technically, even though it's at the end of the sentence, the when part. So if you take two different x values, then their images under f are different. That is the criteria for a one-to-one function. So this is the criteria for a one-to-one function. Okay, so this is the criteria for a one-to-one function. Okay, so let me define a one-to-one function. Okay, a function f is called a one-to-one function if it never takes on the same value twice. That is, f of x1 does not equal f of x2 whenever x1 does not equal x2. Okay, so that's the definition of a one-to-one function. A function f is called a one-to-one function if it never takes on the same value twice. That is, f of x1 does not equal f of x2 whenever x1 does not equal x2. Okay, so this is an example of a one-to-one function. This is an example of a function that never takes on the same value twice, right? See the values here? They are all different. That function does not take on the same value twice. And so you can't say it does because 1 maps to 2 and 1 maps to 2. That does not qualify as taking on the same value twice, because it says when you take two different x values, then their images are different. And so 1 is the same as 1. And so you have to choose two different inputs into your function. And when you do that, then the images are different. Okay? So that's an example of a one-to-one function. And this is an arrow diagram. This is one way to illustrate a function. It's called an arrow diagram. Okay, and so this arrow diagram of this function is an example of a one-to-one function. Okay, so here's a counterexample. Okay, so counterexample. The first counterexample is that if you function g from a to b, this is a counterexample. That's because this function does take on the same value twice. 2 and 3 are two different inputs, but their image is the same. This function takes on the same value twice. And it fails to satisfy this condition that whenever x1 is not equal to x2, that the images are different, right? Because here, 2 and 3 are different, but f of 2 and f of 3 are equal. And so that contradicts that statement there. It contradicts the definition of a one-to-one function. And so this function, g, is not one-to-one. So this is a counterexample. Okay, another counterexample is this one. This is the second counterexample. So if you have a graph here, x-axis and y-axis, okay, so y equals f of x, and so then when you take the height here and the height there, okay, then the height of that point is f of x1, and the height of this point is f of x2, right? So this is a counterexample. This is not a one-to-one function. You have two different x values. x1 is not equal to x2, but the images are the same. x1 is not equal to x2, but f of x1 equals f of x2 because the height of f at those 2 points are the same because they're both on the same horizontal line, right? They're points on this curve here. Y equals f. So this function f is not one-to-one. And so those are two counterexamples for a one-to-one function. There are two functions that are not one-to-one. One-to-one, not one-to-one. Okay. Okay, so there you go. Okay, go. I'm going to erase just the top part here above the definition. So I'm going to keep everything that's below the definition. Okay, next is what's called the horizontal line test. A function is one-to-one if and only if no horizontal line intersects its graph more than once. So horizontal line test. A function is one-to-one if and only if no horizontal line intersects its graph more than once. Okay, so horizontal line test. A function is one-to-one if and only if no horizontal line intersects its graph more than once. Okay? So that means the statement that a function is one-to-one is logically equivalent to no horizontal line intersecting its graph more than once. So here, in this counterexample, this is a horizontal line that does cross the graph more than once, and this is not a one-to-one function. Okay? So to illustrate this situation, let me redraw this picture. Let me just explain what the horizontal line is saying instead of words and as with pictures. So here's the horizontal line. Here's x1. Here's x2. This is y equals f of x. And so, right, so this is not one-to-one. So if a horizontal line intersects the graph more than once, that implies f is not one-to-one by the horizontal line test, right? So you see that? So here, because the horizontal line intersects it more than once, the graph more than once, you can have two different x values whose y values are the same. And so therefore, it repeats the same value more than once. It has this value twice. And so it's not one-to-one. Now going in the opposite direction, if f is not one-to-one, that implies that f takes on the same value twice. And if f takes on the same value twice, at least twice, but twice meaning it takes the same value more than once, that implies that a horizontal line intersects the graph more than once. Okay, so if f is not 1 to 1, that means f repeats the same value more than once, a same value more than once. And so that means there's some horizontal line that will intersect the graph more than once. And where it intersects the graph more than once, those are 2 points where you have 2 different x values and the y value is repeated. Okay, and so this is actually with a picture, and this is actually in words, but it's kind of picturesque, the implications of that. Okay, so that's just illustrating things that the horizontal line test says. Okay, again, it says that the statement a function is 1 to 1 has the same truth value as no horizontal line intersects this graph more than once. The IFF, this is short for if and only if. Okay, IFF is an abbreviation for if and only if, and it means that if you have one statement, if and only if another statement, those 2 statements are logically equivalent. It means they have the same truth value. And so the horizontal line test does not tell you that a statement is true or false. It tells you that 2 statements have the same truth value. That means if you know the truth value of one of these 2 statements, you know the other statement has the same truth value. And so if you know a function is 1 to 1, then you know no horizontal line intersects this graph more than once. If you know no horizontal line intersects the graph of a function more than once, then you know the function is 1 to 1. If you know the function is not 1 to 1, then that's false. There is some horizontal line that intersects the graph more than once. And if you know that this is false, that there is some horizontal line that intersects the graph more than once, then you know it's false, that it's 1 to 1. That's not 1 to 1. So I said that fast, but basically you have 2 statements and they're the same in truth value because of that IFF there, if and only if. Okay? If you know one statement is true or false, then the other statement is the same truth value. Okay, so that's the horizontal line test. Let's keep going. Okay, so example is the function f of x equals x cubed 1 to 1. So example is the function f of x equals x cubed 1 to 1. And so the answer is yes. Okay, so the answer is yes, it is. This function is 1 to 1. And so why though, right? It's not enough. As a mathematician, just giving the answer is not enough. You have to prove it. So this is how you prove it. So the solution as to why it is 1 to 1 is if you take 2 different x values, that implies that the cubes of those x values are different. If you have 2 different real numbers, then their cubes are still different. So x1 does not equal x2 implies that x1 cubed does not equal x2 cubed. Well, x1 cubed is f of x1, and x2 cubed is f of x2. And so that implies that f of x1 does not equal f of x2. So what we just showed is x1 does not equal x2 implies f of x1 does not equal f of x2. Thus f is 1 to 1. Okay? Okay, so that's the proof that that function f is 1 to 1. Another example. Is the function g of x equals x squared 1 to 1? So is the function g of x equals x squared 1 to 1? And so the answer is no. And so why? The solution to that, the proof, is that g of 1 is equal to 1 squared, which is 1. G of negative 1 equals negative 1 squared, which is 1. So 1 does not equal negative 1, but g of 1 equals g of negative 1. Thus, g is not 1 to 1. Okay, thus g is not 1 to 1. Okay, so g of 1 equals 1 squared, which is 1. G of negative 1 equals negative 1 squared, which is 1. So 1 does not equal negative 1, but g of 1 equals negative 1. And so so g takes on the same value twice. Even though 1 is different than negative 1, g at 1 and g at negative 1 are the same. And so g takes on the same value twice, and so g is not 1 to 1. Okay, and so the answer to that question is no, g is not 1 to 1. Okay, okay, so note 1-to-1 functions, they're important and they have inverse functions. Okay, so one importance of 1-to-1 functions is that they have inverse functions. Okay, so when a function is 1-to-1, it has an inverse function. And actually, when a function is not 1-to-1, it does not have an inverse function. Okay? Okay, let's keep going. Okay, so next is another definition. So let f be a 1-to-1 function with domain A and range B. Then its inverse function f inverse has domain B and range A, and is defined by f inverse of y is equal to x if and only if f of x equals y for any y and b. Okay, so definition, let f be a 1-to-1 function with domain A and range B. Then its inverse function, f inverse, has domain B and range A and is defined by f inverse of y equals x, if and only if f of x equals y for any y in B. Okay? So this defines the function, and it says that the statement that f inverse of y is equal to x has the same truth value of f of x equals y for any y in B. So what that means is if you have a function f, let me do a line here. So above the line is the definition, and so I'll illustrate a little bit here. If you have a function, if you have x in your domain set, and f maps x to y, right? What will happen is then f inverse, so f is going to map x to y. Equivalently, you'll have an f inverse that maps y to x. Okay, and so y is in a set B, and x is in a set A. Okay, so whenever a function f maps x to y, it's going to map, f inverse is going to map y to x. Whenever f inverse maps y to x, f maps x to y. Okay, where x is in a domain set A for f, and y is in a codomain set B for f. Okay, here f is 1-to-1. Okay, so you need to have f to be 1-to-1 in order for this situation to happen. Okay, and note the domain of f equals the codomain of f inverse, and the codomain of f equals the domain of f inverse. Okay, so if a function f maps a set A to a set B, that's 1 to 1, f inverse is a function that will map the codomain of f to the domain of A. Okay? Okay, and note f inverse of x, this notation f inverse of x is the inverse of f. Not the reciprocal of f. So f inverse of x does not mean 1 over f of x. It does not mean that. F inverse of x is notation for the inverse function of f. It's notation for this function defined by the definition above this line. Okay, it's another function with this property. It's a function with this particular property. Okay, with this special relationship with the function f. It's not the reciprocal of f. Okay, so that note is important to know. Okay. Okay, so let's continue. Okay. Example. The inverse function of f of x equals x cubed is f inverse of x, which is equal to x to the 1/3, because f inverse of y is equal to f inverse of x cubed, which is equal to x cubed raised to the 1/3, which is x. Okay, so we can say f inverse of x for that f. For f of x equals x cubed, we can say f inverse of x is equal to x to the 1/3 because f inverse of y is equal to x. This is a function that maps the y value of f back to x. So in this example, what's happening is that if you have x and f maps x to y, where y is equal to x cubed, right? F is a function that maps x to y equals x cubed. F inverse is a function that maps y, that y, which is x cubed. F inverse is a function that maps y to x. F inverse of y is x. So f inverse is a function that maps the y back to x. And so that implies that f is in fact, f inverse is in fact the inverse of f. Okay, so we defined f inverse there. We gave it that name. But just because we say, okay, f inverse of x is equal to that, doesn't mean it is the inverse of f, right? It's sort of like we claim it's the inverse of f. We justify saying it's the inverse of f by saying because f inverse of y is equal to x, and making a correct argument for that, right? So we make the correct argument that f inverse of y equals x for that f inverse that we defined. And so since the f inverse we defined satisfies this relationship that f inverse of y equals x, then f inverse is in fact the inverse of f. It's not just a function we named f inverse, it's a function that's a function that is in fact the inverse of that f. Make sense? Okay? Okay? Right? So again, Right, just saying a function is the inverse of a function doesn't make an inverse. You have to justify it, and that's how you do it. Okay, another example. If f of 1 is equal to 5, f of 3 is equal to 7, and f of 8 is equal to -10, find f inverse of 7. Well, f inverse of 7 is 3, because since f of 3 is 7, f inverse of 7 is 3. F inverse of 5, well, f inverse of 5 is 1, because f of 1 is 5, so f inverse of 5 is 1. And f inverse of -10 is 8. Right? Because f of 8 is -10, so f inverse of -10 is 8. Okay, so those are the images under f inverse of 7, 5, and -10. Okay, so that's another example. Okay, good. Okay, notes. Okay, so these are called the cancellation equations. So f inverse of f of x is equal to x for every x in A. F of f inverse of x is equal to x for every x in B. Okay, so if we have f from A to B, then f inverse is from B to A. Okay, so these are called, again, the cancellation equations. Okay, so those two equations are called the cancellation equation. And here, f is a function from A to B, and f inverse is from B to A. Okay, and so an illustration of the first equation, of this equation, I'm going to put a star next to it. So I'm illustrating that equation. And so to illustrate that, I'm going to use arrow diagram. I'm going to use a machine diagram. So if you input x into the function f, the output is f of x. And if you take that f of x and you input it into f inverse, then you will get back x. Okay? And so this is illustrating the relationship between f and f inverse. Okay? That if you input x into f, the output is f of x. And if you input f of x into f inverse, you get back x. And so this is illustrating this equation. F inverse of f of x equals x for every x in A. So this is an x in set A. So an x in set A, you input into f, and then the output of that you input into f inverse. And you get x. Okay? So this is illustrating star. Now this is going to be called diamond. So now I'm going to illustrate diamond over here. If you input x into f inverse first, okay, you input x into f inverse, then f. So you get f inverse of x. Then take f inverse of x and put it into the function f. And then f of f inverse of x is equal to x. And so this is representing this composition of functions, which equals x for every x in B. So here's an input for the function f inverse. So x here is in set B. F inverse, the domain of f inverse is B. And so the input for f inverse has to be an element in B. And just like here, the input for the function f has to be in A because the domain of f is A. Okay? So again, this is illustrating that equation, that's illustrating that equation. Good. Okay, so let's keep going. Okay, so that's illustrating the two cancellation equations. another example. Let f of x equal x cubed. Then f inverse of x, which we already mentioned, is x to the 1/3. The cancellation equations are f inverse of f of x is equal to f inverse of x cubed, which is equal to x cubed to the 1/3, which is x. Okay, so f inverse of f of x is f inverse of x cubed, which is x cubed to the 1/3, which is x. So f inverse of f of x is equal to x, and then f of f inverse of x is equal to f inverse of x is x to the 1/3, and then f of something is that something cubed, so you're going to take x to the 1/3 and cube it. X to the 1/3 cubed, you multiply the exponents and you get x to the 3rd equals x. Okay, so here f of f inverse of x is also equal to x. And so because we have the two cancellation equations here. Okay. Okay. So f and f inverse cancel each other out when performed in succession. Right? So f of f inverse of x is x, and f inverse of f of x equals x. And so the two functions in a sense cancel each other out. Just like adding one and subtracting one cancel each other out, the effect of f cancels out the effect of f inverse, or f cancels out the effect of f inverse. Okay, whatever one function does, if you then do the other function, it just undoes what the last function did. Okay. Okay. Next. So I'm gonna erase this so I have the entire board. Okay, so how to find the inverse function of a one-to-one function f. Okay, so how to find the inverse function of a one-to-one function f? Step 1. Very easy. Write y equals f of x. Step 2. Solve this equation for x in terms of y. And step 3. Interchange x and y. You get y equals f inverse of x. Okay, so those are the 3 steps to find the inverse function of a one-to-one function f. So it's important that you start with the one-to-one function. Okay, so starting with the one-to-one function f, step 1 is write y equals f of x. Step 2 is solve this equation for x in terms of y. So for instance, you might get x equals 2y minus 1. That would be solving for x in terms of y. Step 3 would then be interchange x and y. You get y equals f inverse of x. Okay, and so those are the 3 steps. And so below that, over at the bottom part of the board, I'll apply the 3 steps to find the inverse function of a one-to-one function. So example, find the inverse function of f of x is equal to x cubed plus 2. Okay, so find the inverse function of f of x equals x cubed plus 2. Solution. So example, find the inverse function of f of x equals x cubed plus 2. So step 1, right, y equals f of x. Okay, so step 1 is y equals x cubed plus 2. Here the f of x is x cubed plus 2, so y equals x cubed plus 2. That's step 1, is done. Okay, next step, solve this equation for x in terms of y. Okay, so next, y, you know what I'll do? I'm going to circle this, is that right away we finish step 1. Step 2, we're going to solve for x in terms of y. So y minus 2 equals x cubed. I got the x on one side. And then if I take the cubed root of x, I get x is equal to y minus 2 to the 1/3 power. Right? So now I solve for x in terms of y. Now I solve for x in terms of y. That's algebra. Right? Now step 3, interchange x and y. So y is equal to x minus 2 to the 1/3. And so that's step 3. I interchange x and y. And from here, y is equal to x minus 2 to the 1/3. And so what that means is you then conclude, that implies that y is f inverse of x. So f inverse of x is equal to x minus 2 to the 1/3. Okay? So now that's an inverse function. We found the inverse function of that function f of x. Okay. Okay, so you just apply these 3 steps in that order correctly for a one-to-one function, and you find the inverse of that function. Okay, good. Note the graph of f inverse is obtained by reflecting the graph of f about the line y equals x. Okay? So the graph of f inverse is obtained by reflecting the graph of f about the line y equals x. Okay, so for instance, here's the x-axis, here's the y-axis, and so let's say you have this function. Okay, so this is your function. Okay, sorry. Drill that. Okay, so this is the function f here. That's the function f. And so you can obtain the graph of f inverse by reflecting this graph about the line y equals x. That's the line y equals x. Okay, so here's f. This is the line y equals x. Reflect this about that line, and that's the graph of f inverse. Okay? Right? So you can see how that's a reflection of this about that line. And so what kind of means is if you take a point on this graph and you go into the perpendicular direction towards y equals x, that distance, and you go that same distance that way, and this distance will be the same as that one. And if you go, let's say here, and you go in the perpendicular direction towards y equals x, and you take that distance, and you go that same distance here, and then that is where you end up. And that point is on f inverse. Right? So each of these points correspond with a point on the graph of f inverse. Okay. And so actually this point x comma y of f will correspond with y comma x here. Okay? So when you have a point here, when you switch x and y, you get the coordinates of the corresponding point on f inverse. And so that's why when you have a graph of a function, when you reflect it about the line y equals x, you get the graph of f inverse. Because you get all the points on the curve of f inverse by switching the coordinates of each of the points in F. So all the points on F, if you just switch all the coordinates, x, y to yx, you correspondingly get all the points of F inverse. And graphically, what you're doing is you're reflecting that curve about the line y equals x. That will give you the set of all points y comma x, such that x comma y is on the graph of x, of F. Okay? Okay, so to get the inverse graph of a function, you take the graph of the function and you reflect it about the line y equals x. You then get the graph of F inverse. Okay. So here's an example. Sketch the graph. Sketch the graphs of f of x is equal to 3x plus 5 and its inverse function. So sketch the graphs of f of x equals 3x plus 5 and its inverse function. Okay, so that's this example, and so the solution of this example is the following. Okay, so let's graph the f of x equals 3x plus 5. It's a line, right? It's of the form ax plus b. So when x is 0, the y coordinate is 5. So you get 0 comma 5, right? When x is 0, y is 5. When y is 0, when y is 0, you get a negative here. So without worrying about the exact, do I want to worry about it? Maybe. If the point is negative 5/3. This is negative 5/3 comma 0. Okay, so it's a line that connects those 2 points. Okay, so let's draw a line through those 2 points. This is the line y equals 3x plus 5. That's f of x. Okay, and so then we want to sketch and its inverse function. So to graph its inverse function, take the line. That's the line y equals x, and reflect that line about y equals x. And what you get is, what I'm going to do is I'm going to reflect 2 points about that line. And then, so I'm going to reflect this point about the line here, this will go here. Maybe actually if I draw it closer to what the board is suggesting, maybe it'll okay. So okay, and so that is my approximate graph of f inverse of x. That's f inverse, that's a graph of f inverse. So it's a reflection about f, about the line y equals x. Okay, they'll intersect. If they intersect, they're going to have to intersect on the line y equals x. Okay. Sketch the graphs of the function and its inverse function. And so that's it. So you just reflect it about the line y equals x. Okay, good. Okay, next point. Okay, so theorem. If f is a one-to-one continuous function, defined on an interval, then its inverse function f inverse is also continuous. So, okay, so theorem, if f is a one-to-one continuous function defined on an interval, then its inverse function, f inverse, is also continuous. Okay? So to explain that, explanation. Let me explain it using a picture. Okay? Let me illustrate why this should be true. Okay? So to give you an intuitive idea why this should be true. If f is a so the condition is that if f is a one-to-one continuous function defined on an interval. So let's take an interval from 1 to 2. Okay? And let's make the function look just like that. Okay? That is a one-to-one continuous function defined on an interval. It does not take on the same value twice, and it's continuous. You can draw without lifting your hand, right? It's a one-to-one continuous function, and it's defined on the interval from 1 to 2. Okay. Well, let's graph its inverse function. Okay, well, if you graph its inverse function, what you're going to get is you're going to reflect this about the line here. Now I made this more difficult to draw. So, let me just, there, okay, that's not bad. Okay, so what I did was I reflected the graph of f about the line y equals x, and I got the graph of f inverse. And so if you notice, if you have a function f that's one-to-one and continuous on an interval, when you reflect its graph about the line y equals x, you're going to get, since I can draw this graph without lifting my hand, then I think intuitively makes sense that when you reflect that about this line, you'll get another function you can draw without lifting your hand, right? So you can draw this without lifting your hand, you reflect it about this line, you get another graph that you also can draw without lifting your hand. And what happens actually, this is one-to-one. Okay, so then it's also continuous. So then you have your inverse function, and it's also continuous. Okay? So since you can draw this function f without lifting your hand, you reflect it about the line y equals x, you get another function you can draw without lifting your hand. And that means f inverse is also continuous. So it's illustrating it. It's not a proof, but it's illustrating how the inverse of a function you can also draw without lifting your hand, which means it's a function that's also continuous. Okay? And so that helps you visualize why that theorem works. Okay, so I'm going to erase this for the next thing. Okay, so if f is a one-to-one differentiable function, with inverse function, f inverse, and f prime of f inverse of a does not equal 0, then the inverse function is differentiable function is differentiable at a, and f inverse prime of a is equal to 1 over f prime of f inverse of a. Okay, so this is a theorem. It's called the inverse function theorem. If f is a one-to-one differentiable function with inverse function f inverse, and f prime of f inverse of a is non-zero, then the inverse function is differentiable at a, and f inverse prime of a is equal to 1 over f prime of f inverse of a. Okay, so that's saying that you can find, it's an equation for the derivative of the inverse of f at a point. Okay. Okay, so to explain this one, So given a function with no corner, or kink in it, when a function has a corner on it, it's not differentiable. So for instance, if you were to graph a function and it looked like this, so here there was a corner, there was no smooth transition at this point, it would just be like a corner, then it would not be differentiable at that point because of the corner in the graph. But given a function with no corner or kink in it, when you reflect it about the line y equals x, you still don't have a corner or kink in it. So given a function with kink in it, when you reflect it about y equals x, you get a graph with no corner or kink in it. Okay? So a graph not having a corner in it means that it's differentiable, right? So that means that the derivative is defined at every point. And so once you have a function that's different, one-to-one differentiable, with an inverse function, its inverse is also differentiable. Okay? And this equation tells you how you find the derivative of that inverse function at a point by this equation. Okay? So you just need to know the derivative of the original function f and f inverse of a. Okay? Okay, so let's do an example. Okay, so actually let me stop for a second. This is the inverse function theorem, it's called. Here I'm just calling it theorem. Its name is the inverse function theorem. I'm going to copy that down. Okay. Okay. So another example. If f of x equals 2x plus cosine x, find f inverse prime of 1. Okay, so solution. So just like other theorems, in this class I won't require you to show all the conditions of a theorem satisfied to use it. So let's just we're going to use the inverse function theorem here. So f inverse prime of 1 is equal to 1 over f prime of f inverse of 1. Okay, so what is f inverse of 1? Well, when does f of x equal 1? F of x equals 1. If I plug in x equals 0, I get 2 times 0 plus cosine of 0. So f of 0 is equal to 2 times 0 plus cosine of 0. And that's equal to 0 plus 1, which is 1. So f of 0 equals 1. So f inverse of 1 is equal to 0. That's what I wanted. Okay? So what I did was I found a value of x such that f of x equals 1. F of 0 equals 1. That means f inverse of 1 equals 0. So f inverse of 1 is 0. So I found f inverse of 1, and I plug that in here, and you get 1 over f prime of 0. Because f inverse of 1 is 0. Right? So let's find f prime of x. F prime of x is the derivative of that function, which is 2 minus sine x. The derivative of 2x is 2, derivative of cosine x is minus sine x. F prime of 0 is just plugging in 0 into that function. So you get 2 minus sine of 0. 2 minus sine of 0 is 2 minus 0, which is 2. So f prime of 0 is 2. And so you just plug that in, you get 1 over 2. So f inverse prime of 1 is 1/2. Okay? And so that's using the inverse function theorem to find f inverse prime of 1. It's 1/2. This is the sine group here. Okay? So thanks for watching this video, and I'll see you next time.